This is a good time to define the central limit theorem, and just follow me on this. I don't think I'll press you on a definition of the central limit theorem, but I do want you to know the first two things it asserts, and really the only two things. For any population with a mean of mu and a standard deviation of sigma, the distribution of sample means for any sample size n will also have a mean of mu, the same mean as we spoke of before, like 5, and a standard deviation that's calculated like this: the population standard deviation divided by the square root of n, whatever n is, whether it's 2 or 256. And this will approach a normal distribution. The distribution of sample means will approach normal as n approaches infinity, and not to split hairs, particularly when it surpasses the number 30. The value of this theorem comes from two simple facts. First, it describes the distribution of sample means for any population, doesn't matter what it is. Could be talking about needles on an evergreen tree, or heights of people, or IQ scores. Second, the distribution of sample means approaches a normal distribution very rapidly. By the time that sample size gets up to about 30, it's always normal. And we never consider too many contrary examples. We don't sweat it if it's below 30. Note that the central limit theorem describes the distribution of sample means by identifying three basic characteristics: the shape being normal, the central tendency where the means are one and the same. The mean from the population is also the mean for the distribution of sample means, and variability. And we'll speak of this idea of a standard error here coming up very shortly. It's been observed that the distribution of sample means tends to be normal. It's almost perfectly normal if either of the two following conditions is satisfied. The population from which the samples are selected is normal, and the number of scores in each sample is relatively large. There's a little caveat I guess I'd tell you about. This is trivia. I won't test you on it. But even if the population from which the distribution of sample means comes is not normal, the distribution of sample means will be normal if the sample is 30 or more. How about them apples? However, if it's a normal distribution, we don't have to worry about the sample size. And for our purposes, we're not going to worry about it at all. So here is a calculation. The standard deviation of the distribution of sample means is called the standard error. I'm almost disinclined to use the phrase standard error because what happens? You forget what it is. I really actually like to say over and over again the standard deviation of the distribution of sample means. The standard error provides a measure of how much distance is expected between a sample mean and the population mean, which is greatly affected by sample size and the variability of the original population, as we'll see here shortly. I want to get into some calculations, of course. Pardon me, let me just read two more definitions and we'll get on to some practical stuff. The standard error describes the distribution of sample means. It provides a measure of how much difference is expected from one sample to another, as we just said. When the standard error is small, the sample means are close together and have similar values. Do you know one context in which the standard error will be small? When the sample size is large. If the standard error is large, the sample means are scattered over a wide range, and I can't wait to talk about examples of those. Standard error measures how well an individual sample mean represents the entire distribution. It provides a measure of how much distance is reasonable to expect between a sample mean and the overall mean for the distribution of sample means. However, because the overall mean is equal to mu, as we've said, the overall mean of the distribution of sample means is mu, the standard error also provides a measure of how much distance to expect between the sample mean and the population mean mu. I'm not going to press you on these paragraph-long assertions. When we get into it, when I show you a few problems here, I think it'll become clear what we're talking about. We're going to go to extremes, as Billy Joel said. Small samples and large samples, and really flesh this out. So one last thing I want to tell you, and we'll pick up with the next clip. Earlier, we predicted, based on common sense, which is actually two words, that the size of a sample should influence how accurately the sample represents its population. Doesn't that kind of make sense? I hope it does. We'll speak of that more here shortly. A large sample should be more accurate than a small sample. Of course it should be. If I wanted to speak of the attitudes of SFA students, wouldn't I be better off sampling 100 people randomly than 4? Couldn't 4 people be aberrant? Couldn't they be unusual? But 100 people, on the other hand, are more likely to be representative of the entire population of 14,000 SFA students. In general, as the sample size increases, the error between the sample mean and the population mean should decrease. Of course it should. And this is the law of large numbers, which literally states that the larger the sample size, the more probable it is that the sample mean will be close to the population mean. And again, this is not like trying to remember the particulars of what the Magna Carta said, that you have to memorize these facts. We'll get into it, and these trade-offs will become apparent. I'm looking forward to getting into some problems that I've photographed, and these principles will become clear.